Hey everybody, thank you and welcome. We have a great talk today. I just want to ask everybody for one favor, if you could take a moment and please silence your cell phones. I know we were all just at lunch and getting our messages. If you could put those on vibrate, I'd really appreciate it. All right, so today's talk is going to be towards discovering remote code execution vulnerabilities in Apple FaceTime. So if you guys could, please give a warm welcome to Tao and Tele.
Thank you. Thank you very much for coming to our talk. And my name is Tele Wang. This is my colleague Tao. And both of us are from Team Pangu. We have been working on iOS security research for a very long time. And today this talk is about FaceTime security. And so motivation. We knew that actually now messaging apps has become a very hot research target, and no matter the bug bounty programs or other rumors, and as demonstrated by other researchers, both WhatsApp and message could be remotely compromised. Actually, a few months ago, after we read the blog post by Google project GP0 and about how to fuzz WhatsApp and iMessage FaceTime, we realized that actually the code quality of such messaging apps is not as good as we expected. So we decided to take a look, especially FaceTime. So the scope of the talk, and in this talk, we are going to show you the code execution flows for FaceTime call initialization and the connection. And we will analyze the attack surface along these execution flows. And we will show you a lot of very interesting bugs on these execution flows. And, but the talk will not go to the details of the protocol families used by FaceTime, like SAP, SDN, RTP, SRTP, and so on. Also, the talk will not talk about how the audio or video streams encrypted or decrypted. Please refer to other related work for more information. And this is the outline of the talk. And Tao will continue to introduce how a FaceTime call is initialized and connected and analyze the attack surface. After that, I will show you some very interesting bugs and conclude the talk. Okay.
So this is the FaceTime Outlook running on macOS. It looks like it is a single application, but in fact, FaceTime consists of multi-process. FaceTime app provides the basic UI framework, and the core service D is responsible for provide the function on the left side. The main features associated with our talk is these three. First, core service D will manage the call status of FaceTime. Second, core service D will be responsible for respond to the UI triggered events. And the last, core service D will provide a communication bridge between AV Conference D and Identity Service D. The function on the right side is powered by AV Conference D on macOS or Media Server D on iOS. They will produce and handling the FaceTime video or audio streams. So we can consider that FaceTime consists of the three major components. So this is when a user tries to make a FaceTime call, the user will need to click the button on the left side. Then FaceTime app will generate a notification. We can call it a notification call. Then the notification will be handled by the core service D. Core service D will call the function perform start call action. And then core service D will invoke the corresponding handler to create a new invitation. So core service D will send an explicit message to AV Conference D to get the invitation date, as through the function prepare with configuration. The invite date consists of media blob, SKE blob, and some other informations. Media blob contains the configuration for audio and video streams. SKE blob contains the encryption and decryption parameters for audio and video streams. After AV conference D generates the blobs, it will send back to COSOSD. COSOSD then will continue to encapsulate more information. After that, COSOSD passes the invitation date to IdentService-D for further encapsulation. IdentService-D, or we can call it IdentService daemon, is a system process that handles credentials for a variety of services, including iCloud and iMessage. It also connects to computers and iOS devices on your local network to coordinate phone calls across multiple devices. So IdentService-D will continue to encapsulate more information and then passes it to APS-D. APS-D is so we can also call it Apple Push Service daemon, is responsible for sending and receiving push notification. APS-D also maintains a reliable and a secure connection to Apple server. So APS-D will continue to serialize the whole invitation date into an struct called APS message, and then send it to Apple server. When an endpoint sends a notification to Apple, Apple does not simply forward it to destination. Instead, Apple will modify payloads in the notification. So it's important for us to find out which state is we can control. So we will comparing the notification sent out and the notification received on the remote side. So we find out some of data we can control. Apple server now will forward notification to the callee endpoint according to the content of the APS message. The remote APS-D will deserialize the APS message. This is how it looks like in LDB on the left side, right side. We send a breakpoint in APS-D message deserialization function in a debugger and checks the received notification. The key APS protocol command is 10, and the value of APS protocol payload and APS protocol topic hash here is binary, which is important for the later work. APS-D will, according to the APS protocol topic hash and APS protocol command received, and delivers the payload of the notification to IdentService-D. We also set breakpoints in IdentService-D and check the received invitation. It looks like the picture on the right side. The value of key C is the most important. It indicates that which function will be invoked to handle this notification. As in white, the C is 232. So the notification will be handled by the function process incoming invitation with payload. And then IdentService-D will continue to forward the date to COSOSD. COSOSD will pass binary payload through the function, and after pass, it looks like this. It looks like an NS dictionary. And then COSOSD will continue to forward the blobs to AV conference D or media server D on the remote side. And we can see here the AV conference D or media server D of the remote side has received the blobs come from the local side. And now UI will pop out to tell you that you have a new FaceTime invite. Do you want to accept? And we click the accept button. It will generate a UI notification. We can call it UI notification accept. So the UI notification will be sent to call service D. And the call service D will also handle the notifications through another handler function and do almost the same thing just we did on the local side. It will get the invite date. It also called invite date because it has media blob and SK blob, and get it from AV conference D and encapsulate more information and send it back to ident service D. Ident service D will pass the date to APS D, and APS D will encapsulate, it will serialize the APS message and send it to Apple server. Apple server will forward the notification to our caller APSD. Caller APSD will deserialize the APS message and pass the date to ident service D. And now the value of KC is 233, which means this notification is accept message and tell our local side that the colleague has already accepted your invite. And ident service D will pass the date to call service D. Call service D will pass the media blob and SK blob of remote side to AV conference D. And now the information we need to make a connection has been changed. And meanwhile, ident service D will create sockets for session-based connections. And another notification called Quick Relay. Apple Quick Relay server will coordinate caller and callee to build a direct connection. But we don't give a detail introduced here because a lot of dates in Quick Relay notification is not controllable. And now the caller and the callee can see and hear each other via FaceTime. But in fact, and now all the data is transformed through the socket with UDP or TCP. Ident service D is responsible for the first layer packet handling and packet redispatching. This function IDS UDP link process incoming packets will call the function receive message and pass the date to IDS global link. And then this function ident service, and in this function ident service D will identify system message according to the magic number, which is 42A41221. And then ident service D passes system message to a handler. The handler will further call different handlers according to different system message type. Besides the message, many other type of packets also handled by ident service D itself. The rest of packets will be distributed to different processes, such as AV conference D. And this packet like RTP packet or RTCP packet. So RTP packet handler is in another process, but at firstly it looks the same. IDS UDP link process incoming packet will call receive message to get data from UDP from socket, and then the packet will pass to IDS global link. And the IDS global link will find this packet will not be handled by ident service D. So he will pass the date to his delegate class called IDS link manager. And the IDS link manager will pass the data to its delegate class called IDS session. And this function IDS session, this class IDS session will transfer data to AV conference D through a series of undocumented system call, which is OS channel or OS Nexus families. And this is the finally implementing of underlying network. So that is all of the reserve engineering. And let's see the attack surface. The code for notification processing and delivering forms zero-click attack surface, which means the attacker can send a notification to the colleague, goes through Apple server and APS-D and identity service D, and then core service D, as last AV conference D or media server D. That's the zero-click attack service. And the code for socket packet processing and delivering forms one-click attack service. After FaceTime call is connected, attacker can directly send packet to identity service D, and identity service D will pass the packet to AV conference D. Identity service D can further dispatch message to other service according to topic and commands, and open new attack service. This is some other attack service we found, like iMessage, remote desk port, phone continuity, and something like that. It includes also one-click or zero-click attack service. And next.
Okay, next I'm going to show you some very interesting vulnerabilities. And the first one is a potential info leak on the zero-click attack surface from APS-D to identity service D. Why we call it a potential info leak, I will explain it later. And so the reason we noticed this issue is this. So when we send an invitation out, we notice that actually the invitation dictionary has a UUID. The UUID just some random numbers without any special meanings. But we found a way to trigger the receiver. We can force the receiver to reply a message. In the replied message, we found the same UUID. So basically, no matter the receiver accept or decline or notice the FaceTime call, we can force the receiver to generate a reply message. And so far, nothing special. But if you look at how the receiver passed the UUID, you will find something interesting. So after an invitation is received, identity service D will try to pass the dictionary. And the first step is it tries to fetch the U in the dictionary. U is the key. And if the value object is NS data, and it will pass the NS data to a function called GWUUID push object to string. You don't have to read the whole code. The function is supposed to convert or dump the NS data buffer into a local stack-based buffer, and then convert the local buffer to a CF string. But the question is, first, there's no check on the length of the NS data, the UUID. So second thing is the local buffer is not initialized. So what would happen if the UUID is less than 16 bits? So it will cause a kind of uninitialized memory leak because we can force the receiver send the UUID back. So what we hope to do is this. We implemented a very simple POC. We hope to see this. We send some UUID very short, like 4 bytes or 8 bytes, and we want to get some leaked value on the stack. But when we really do that, we found something very interesting. So when the UUID is very short, for example, less than 16 bytes, we don't know what happened on the Apple server. It seems Apple server had kind of validation on the UUIDs because on the receiver side, the UUID just disappeared. So there's no UUID in the dictionary. So apparently the Apple server filter out the UUIDs. We don't know Apple does that on purpose or not. Anyway, it blocks the info leak. And also we don't know when Apple server started to filter out the invalid UUIDs. Okay, so that's a potential info leak. Maybe you don't think that's very interesting. Now we move to some very juicy bugs, hyper overflows. And as Tor already mentioned, if a FaceTime call is connected, that means the attacker is able to directly send UTP packets to the remote identity service D. And let's see what happened there. So Tor already mentioned that actually identity service D is responsible for handling a kind of message called stem message. And identity service D find or identifies that kind of message by magic number matching. So if you just drop a UDP packet and offset 4, you put a magic number like 42A4, blah, 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 it will trigger the stem message parser. And what identity service D do is this. So it will first deserialize the UTP packet into a IDS stem message object. This deserialization parser is okay. We didn't find bugs here. And so the deserialized IDS stem message, the format or the structure is also very simple. It has a type and a length, and the IDS stem message may have like at most 20 attributes. The attribute is just some buffer, just copied from the UTP payload. So basically, they are totally under the attacker's control. So according to the type of the IDS stem message, identity service D will continue to invoke different handler functions. And in the case, the type is 0x17, a function called process data indication will be invoked. Inside this function, it will first try to get attribute from the IDS message. The type of the attribute is 19. And so get attribute is very simple. It's just copy the attribute from the IDS message to a local buffer. So basically, you can just imagine that it's just copy the UTP payload bytes to a local buffer. You will see a memory copy here, but nothing wrong here. So this memory copy, okay, maybe this is only correct memory copy you will see in this presentation. Okay, now the local buffer is totally under attacker's control. What this local buffer is used is this. This local buffer will be used to deserialize into another object called IDS global link message. And this path is also very simple because the format is like type, length, and payload. And the type is 2 bytes, and the length is 2 bytes, and the rest is the payload. So the path should be easy. But if you look at the case like F, it will go to a function called read IDS glink attribute binary data. Inside this function, what would happen is, there is the memory copy. Okay, this memory copy is very, very tricky. If you look at the size parameter, it's directly read from the attribute buffer, the local buffer. It's totally under attacker's control. And so it's a very typical heap overflow issue. The source buffer is the raw packet UTP payload, and the size is read from the payload. So if you do a fuzz here, like you randomly generate a stem message, and you can easily trigger a crash like this. So this is a crash log on Mac OS, I think. And you can see the mem copy trigger the crash. So we just do a little bit modification to the POC, make some kind of heap layout manipulation, and we can easily overwrite the IAC pointer of adjacent objects, and we can trigger a crash like it try to access 41, 41, 41. That means the next object, the adjacent object's IAC pointer is already controlled. So how to exploit it? Please refer to Neil's work, Modern Object-C Exploitation, for more details. In short, it's not that hard. Okay, now let's move to another very interesting bug, stack overflow issue in RTP parser. So you may ask me, okay, come on, stack overflow, is still exploitable? Let's see. So when a FaceTime call is connected, so video frames will be transferred between each side. So if a video frame is very large, it may split into multiple RTP packets and send to the other side. The receiver will reassemble such RTP packets into a video frame. This picture shows how the video frame and RTP package is organized. So there's a list for different frame, and for each frame, there's a list for different RTP packet. I want to emphasize that when any service D receives the RTP packet, or AV conference D handles the RTP packet, there is a very restrict check on the RTP packet to make sure the length field in the RTP packet equals the real size of the payload. So there is a very restrict check. But the question is, FaceTime uses a mechanism called forward error correction, FEC mechanism, to minimize the influence of packet loss. So in the case, for example, a frame is split into 8 packets and 1 packet is lost, the receiver will try to rebuild a new RTP packet based on the FEC information encoded in the original, the rest of received RTP packets. However, the error here is this. For the repaired or the newly generated RTP packet, the length field is just copied from the FEC header that is totally under attacker's control without any validation. So we don't have to go to the details of the code. Anyway, so when the frame is scheduled to be processed, it will trigger such a kind of execution flow, assembly frame, and finally there's a memory copy. It's a very typical Stack Overflow issue, and it tries to copy heap buffer to a local stack buffer, and the size is under attacker's control. So back to the question, is Stack Overflow exploitable on iOS in 2019? So we know that the most typical way to prevent Stack Overflow issues is stack cookie or stack canary. The idea is this. So between return address and the local variables, the compiler will insert a stack canary. Before the function returns, it will compare the cookie or the canary on the stack against the value on the heap. If there is a mismatch, just crash the program. That means some kind of Stack Overflow happened. So it works very well. It can prevent a lot of typical Stack Overflows. But let's look at the function assemble frame. Okay, if you are not familiar with these binary instructions, don't worry, I will explain it for you. So these instructions is used to, okay, if the function is called, the return address already on the stack, and these instructions are used to save some registers, and these instructions in the red box is used to allocate local variables. And this instructions is used to insert the stack canary. Okay, you may find something wrong. The stack canary is placed below local variables. So what would happen if a Stack Overflow happens? It looks like this. After the Stack Overflow happens, nothing is wrong with the stack canary. So you will see like this. This is crash log on iOS in media server D. You can see after the Stack Overflow, the PC is totally under control, and a lot of registers are also under control. So if you want to ask me how to exploit this vulnerability, I would suggest you to read the paper entitled Smash Stacks for Fun and Profit, published in 1996, I think. Okay, we reported to Apple, it's already fixed in the latest version, but we found something more interesting. This function is not the single victim. We find a lot of other functions in different modules have the same issue. The stack cookie is placed in the wrong position. So we suspect there is a compiler bug behind the Stack Overflow. So finally, I think Apple security team pinpointed the compiler issue and reported to LLVM. So if you were an app developer, remember, update your FaceTime and also update your compiler. Otherwise, your apps may also have the Stack Overflow issues. Okay, now let's move to other attack surface. And Paul already mentioned that actually Identity Service D is able to deliver notifications or network packets to a lot of different system services like MSH, remote desktop, and the phone continuity. And we analyzed some of them, and we found some very interesting bugs too. For example, let's see phone continuity. Phone continuity allows to make and receive calls from your Mac or iPad if these devices are close to your iPhone and they are logged in with the same Apple ID. So apparently you can make a call with your Mac if it's close to your iPhone. That means there must be some data channel between your Mac and your iPhone. So we reverse engineered that pass, and we found that also handled, first layer packet also handled by Identity Service D. And if you look at this execution path, it will finally go to a function called IDSOC ADDR wrapper. And again, you don't have to read the whole pseudo code. You just remember there's a memory copy. It tries to copy socket address structure, which is copied from which is inside a UDP payload to a heap object. And the checks before the red box seems to check they are doing the socket address family checks like it's UDP or TCP protocol. But there's no checks on the length or the first bytes in the socket address. So if you are familiar with iOS security research, you may remember that last year, Embeer from GP0 had a similar bug in the kernel. So in the MP TCP part. So it also tries to copy a socket address to a heap buffer. The question is the maximum length or the size for a valid socket address is 0x80. But the maximum length could be specified in the memory copy is 0xFF. So it's also a typical heap overflow. It's not hard to exploit that. So in this talk, we only shared some typical bugs like stack overflows or heap overflows in such attack surface. Actually, during the reverse engineering process, we found a lot of trivial bugs like type confusions and some after of boundaries. And they are not mentioned in this talk, but I encourage you guys to take another look. Maybe you can find more interesting things. Okay, conclusion. First, after we do this, we find FaceTime's implementation needs significant improvements, a lot of trivial bugs there. And the attack surface exposed by messaging interface, like a lot of interface in Identity Service D, need more attentions. No matter Apple security team or other security researchers, you can find a lot of juicy bugs there maybe. And the most surprising thing is and the most interesting thing to me is that the most typical stack overflow may still happen and may still affect iOS now. Thank you.